Hi guys, so in this last video we're going to look at the behavior of gas particles, and the first two vocabulary words are diffusion versus effusion, and they talk about how gas particles move. So diffusion is how they move in a vacuum, and they're always going to go from an area of high concentration where there are a lot of gas particles to an area of low concentration where there are not a lot of gas particles. So they always try to get away from each other. Effusion is more specific. It's when gas is in a container and then there's a little pinhole made in that container, and the gas particles are going to escape through that pinhole, right? And the important thing to remember is that the lighter the gas is, the faster the rate of effusion is. Okay, so in these two diagrams here, we have helium in one container and ethylene oxide in the other. Helium is a much lighter gas, 4 grams per mole, right? Versus if we add up all of those masses for ethylene oxide, it's going to be much heavier. Look at the number of particles that were able to pass through the pinhole versus the number of particles over here. Okay, so the lighter the gas, the better it's going to be at moving and spreading out. So we can actually calculate these rates. I like to, in this formula, I like to always make the lighter gas, gas 1, and I'm talking about masses on the periodic table, guys, and I like to make the heavy gas, gas 2. I'm using a different stylus and it's awful. And then that's equal to the square root of the heavier gas divided by the lighter one. So gas 2 goes on top, gas 1 goes on the bottom, and it's the square root. So now this is going to tell us how many times faster. If we plug the numbers in this way, how many times faster the lighter gas moves. Okay, so let's look at an example problem. Now they have to tell us what the gases are so that we can look up their masses. So helium has a mass of 4 grams per mole, and oxygen has a mass of 32. So I want to know how much faster helium moves compared to oxygen. I'm putting the light one on top and the heavier one on bottom. So now when I go to do my division, I put the heavier one on top and the lighter mass on the bottom. And when you divide those, you get 8. And when you take the square root of 8, you get 2.8 times faster. And it's going to move faster because it's lighter. Okay? Next question, how long will it take helium to travel the same distance if it took O2 3 hours? Okay, so this is just doing a simple division. How many times does 2.8 go into 3? So helium is going to be able to travel the same distance in only 1.07 hours, where it took oxygen 3 hours because it's much slower. Okay, so these are the kinds of questions you'll see with this formula. All right, kinetic molecular theory. So we're going to look at we're going to look first of all, at a video of this tomorrow, and it's going to show you an example of diffusion and effusion. We're also going to look at a cool simulation that shows you how gas particles behave. As far as stuff you have to memorize, the KMT is the kinetic molecular theory, and it explains the behavior of an ideal gas. So in perfect conditions, how do gas particles behave? So we use ERNI to remember these 4 things. E stands for elastic collisions. So when particles collide, instead of losing energy and eventually stopping motion, they just keep going and going and going. R stands for random straight lines. And you guys will see that in the animation tomorrow that I show you. N stands for no IMFs. Now, we know that that's not really true. All particles have intermolecular forces. In a gas, they just happen to be very, very weak. But this theory, again, explains ideal behavior. So no IMFs would make our gas very able to spread apart. And I stands for insignificant or negligible volume. Okay, so if we imagine drawing a particle diagram of a gas, we're talking about the size of the particles compared to the space between them. They're so small. So looking at a container, it's hard to say, oh, that's the volume of the gas, because the particles of the actual gas are very, very small. They're just really, really spread out. Okay. All right. So real gases don't always follow this behavior. Like I said before, it's not true that they don't have IMFs. It's also not true that they don't have volume. All matter has volume. So these are two parts of the theory that are not necessarily true, but these assumptions make our calculations easier. What would make a real gas behave the most ideally? If it has a low mass, and it's a nonpolar molecule, it's more likely to have weaker IMFs. So two examples are H2 and He. Those are our best gases. What we can do to help this along is increase the temperature and lower the pressure. And by doing that, we're taking a gas that maybe doesn't have a low mass or maybe doesn't have a nonpolar structure, and we're helping it behave ideally. Okay, so we will talk about these two graphs in class tomorrow and what they actually show you. But for now, I'm just going to give you one or two more questions, and I'll see you tomorrow.